Find E bar. Next problem. Find E bar at the origin. If the following charge distribution are present in free space, point charge 12 nanocoulomb at P206, uniform line charge density. Three nanocoulomb at x is equal to -2, y is equal to 3, uniform surface charge density .2 nanocoulomb per meter square at x is equal to 2. So we have to find the E bar. Now here we have to calculate E bar separately due to each charge distribution. So first we write here, we calculate E bar separately due to each charge distribution. So first is E bar due to point charge, E1 bar. So here we have to calculate the E bar due to the point charge Q at point P206. So here calculate E bar due to point charge Q at P206 at origin, and we draw the diagram for this. This is y, this one is x-axis, and this is z. So here it is x is equal to 2, this is point of origin, it is z is equal to 6. This is vector r bar, this is point Q206. So first we find the vector r bar. So it is equal to 0 minus 2 ax bar plus 0 minus 0 ay bar plus 0 minus 6 az bar. So r bar is equal to minus 2 ax bar minus 6 az bar. Now we calculate mod of this, that is equal to minus 2 square plus minus of 6 square, so it is 4 plus 36, that is square root of 40. So we can write here unit vector, that is ar bar is equal to minus 2ax bar minus 6az bar square root of 40. Now we have the value of this vector ar bar. Now we can calculate er bar due to the point charge. So now E bar due to point charge. So E1 bar is equal to Q divided by 4 pi epsilon 0 r square into AR bar. Now value of Q is 12 nanocoulomb. So it is 12 into 10 raised to minus 9 divided by 4 pi 8 into 85 into 10 raised to minus 12 into R is 40. So it is so by solving this part of the equation we get 0.852 and multiply it inside, so we get this one, this answer, volt per meter. So this is E1 bar. Now second is E due to the line charge E2 bar. Second part is E due to line charge E2 bar. Now the line charge distribution, we have to draw the diagram for the line charge distribution and the point P at the origin. So this is X, this one is Y, and this is Z. This is point of origin 0 0 0. This is, here it is Y is equal to 3 and here it is X is equal to minus 2. It is given in the problem. So this is P dash point, that's minus 2 3 0. This is vector R bar. So here the given plane is, so here a perpendicular is drawn from the origin and it meets the line charge density at P dash. So we write here perpendicular drawn from origin and it meets line charge density at P dash is equal to minus 2 3 0. So first we find the vector R bar, 0 minus minus of 2 AX bar plus 0 minus 3 AY bar plus 0 minus 0 AZ bar. So it is 2 AX bar minus 3 AY bar. Next is we can find R, 2 square plus minus of 3 square. So it is 4 plus 9, it is square root of 13, and AR bar is equal to 2AX bar minus 3 AY bar divided by square root of 13. Now next part is E bar due to the line charge. We have to find the value of E. Now E bar due to line charge density, it is given by E2 bar is equal to 2 pi epsilon 0 R A R bar. So this value is 3 into 10 raised to minus 9 . So by solving this part of the equation and the answer is multiplied with this bracket 2x bar minus 3ay bar, we get 8.29 ax bar minus 12.44 ay bar per meter. So it is E2 bar. Now first part of this problem is E bar due to the point charge, second one we calculate E bar due to the line charge, and third we have to calculate the E bar due to the surface charge. So E bar due to surface charge. Now for that we have to draw the diagram. This is x, y and z. This is point of origin 0, 0, 0. Now for surface charge they have given x is equal to 2. So this is the diagram for the E bar due to the surface charge. So here the given plane, in the given problem, value of x is given, so the plane is parallel to the yz plane. So we have to find the value of E3 at the origin, that is at point P, but point P is backside. So E bar due to the surface charge density formula is this. Value is given, that 0.2 nanocoulomb. So by solving this we get E3 is equal to minus 11.29 AX bar volt per meter. Now total E bar. So total E bar is E bar equal to E1 bar plus E2 bar plus E3 bar. So it is minus 0.852 AX bar minus 2.56 AZ bar plus 9 AX bar minus 12.44 AY bar minus 11.29 AX bar. So final answer is minus 3.852 AX bar minus 12.44 AY bar minus 2.56 AZ bar volt per meter. Next problem. A charge distribution is placed. This problem is asked in exam. Also the previous problem was asked in the exam. This one also. So a charge distribution is placed in Z is equal to minus 3 meter in the form of square sheet defined by minus 2 less than equal to x less than equal to 2 meter, minus 2 it has a charge density of is equal to 2 into x square plus y square plus 9 raised to 3 by 2 nanocoulomb per meter square. So find electric field intensity, that is E bar at origin. So for solving this problem, there are 3 steps. First, locate the given sheet in coordinate system. Second step is consider a small charge dq to on the surface and draw the vector from dq to the origin, that is at r bar. And then calculate a small, that is unit vector ar bar. And the third step is use the basic equation for the dE bar, and then integrating that dE bar we can calculate the E bar. So first is we draw the diagram for the given charge distribution. This is y, this one is x, y and z plane. This is point of origin 0, 0 and 0. This is small charge dq. And this is vector r bar from dq to the point of origin. Now the charge distribution is in z is equal to -3. Here the charge distribution is in z is equal to -3 plane and xy coordinates are varying. So consider small charge dq on charge distribution. So its coordinate are x, y and -3. Now second step 2. So here we have to remember that this is not an infinite charge distribution. So we cannot use the direct formula of E bar due to the infinite charge distribution. So we have to calculate E bar at point origin, that is 0, 0, 0. So we have drawn the vector r bar from dq to point of origin, that is at 0, 0, 0. Now we have to find the value of that r bar. So it is r bar is equal to minus x ax bar minus y ay bar plus 3 az bar. It is 0 minus x ax bar, 0 minus y ay bar, and 0 minus of minus 3 is az bar. So by solving it we get this answer, and it is square root of x square plus y square plus 3 square is 9. So unit vector ar bar is equal to divided by square root of x square plus y square plus 9. Now next is step 3. Step 3. So here we are using basic formula. Use basic formula. We cannot calculate directly E bar due to because this is not an infinite charge distribution. So first we have to calculate dE bar. It is equal to dQ divided by 4 pi epsilon 0 r square AR bar. But here dQ is equal to what? It is ds. So now how to obtain that ds? So in Cartesian coordinate system, x is denoted by dx, y is denoted by dy, and z is denoted by dz. So here z is equal to minus 3 is given and it is constant. So delete dz and take multiplication of dx and dy. So here ds is equal to dx dot dy. So we have to consider it. So dq is equal to ds is equal to rho s dx dy. So given in the problem, dx dy into 10 raised to minus 9, as this value is in nanocoulomb. This is equation 1. Now put these values in equation 1. This is equation 1. So we can write dE bar is equal to 2 into x square plus y square plus 9 raised to 3 by 2 dx dy 10 raised to minus 9 divided by 4 pi into 8.85 into 10 raised to minus 12 into x square plus y square plus 9 into minus x ax bar minus y ay bar plus 3 az bar divided by square root of x square plus y square plus 9. So by solving this equation we get the answer by solving mathematical terms. So it is 17.79 dx dy x square plus y square plus 9 raised to 3 by 2 divided by x square plus y square plus 9 raised to 3 by 2 into minus x ax bar, so y ay bar Now, similar to the derivative of infinite surface charges density, Now we write here similar to, this is dE bar. We write here similar to derivation of infinite surface charge density due to symmetry AX bar and AY bar, components get cancelled. Due to the symmetry AX bar and AY bar, components get cancelled. So it is dE bar is equal to 79 dx dy 3az bar. So by solving it, it is 53 dx dy az bar. Now we have to calculate E bar. So we integrate above equation and we get E bar is equal to 53.93 integration for dx value goes from -2 to +2, for dy value goes from -2 to +2, dy az bar. So it is 53.93 x -2 to 2 y -2 to 2 az bar. So by solving it we get 862.88 az bar volt per meter. This is the answer. Next is problems on volume charge distribution. So first problem is volume charge density is given by, it is 10 into e raised to minus 1000 into e raised to minus 100. Then find the maximum value of rho v in the region and z is in between 0 and 0.01 meter. Second part of the problem is find the voltage charge contained in the first octane where x, y and z are positive. Now what is given in the problem? Given is that in the problem they have given value of this, that is 10 into e raised to minus 1000 e raised to minus 100 z coulomb per meter cube. So here the variables are r and z. So we write here variables are r and z. So maximum value rho v is obtained when r is equal to 0 and z is equal to 0. Therefore rho v is equal to 10 coulomb per meter cube. This is the first part of the problem. they have asked the maximum value. It is obtained when both r and z is equal to 0. Now the next part of the problem is we have dq is equal to rho v into dv. So by taking the integration, we can write q is equal to integration v into dv. This is equation 1. Now we have to obtain the value of this dv. So the given coordinates are r, phi and z. That means it is cylindrical coordinate system. As r, phi, z is given in the problem, it is cylindrical coordinate system. So the variation in the coordinates can be r can be written as dr, phi can be r d phi and z is dz. Now dv is a differential volume and it is a multiplication of 3 components. So we can write dv is equal to dr r d phi dz. So we can write it as r dr d phi and dz. This is our equation 2. Now put the values of rho v and dv in equation 1. Put values of dv and rho v in equation 1. So equation 1 will be q is equal to integration value of rho v is 10 into e raised to minus 1000 r e raised to minus 100 z into dv is r dr d phi dz. So this is equation number 3. Now the volume integration is a triple integration. So we have to calculate q in first octant. We write here volume integration is triple integration. So calculate q in first octant. Where variations are value of r is in between 0 to infinity, value of phi is in between pi by 2 to 0, and z is so the equation will be by taking integration 10 constant outside the integration 0 to infinity r e raised to minus 1000 r dr phi 0 to pi by 2 d phi and z 0 to infinity e raised to minus 100 z dz. So by using integration by parts, for first integration we write here using integration by parts rule. By parts, for first integration we can write here q is equal to 10 This is by part rule which was covered in mathematics. Here we substitute infinity and 0 at this place, so it is so by solving this on calcium we get answer 157.07 nanocoulomb. So determine the total charge on the line having values of x is in between 0 to 5 and rho L is 12x meter. So on the line having these values and on the cylinder having these values. So first we write what is given. So given is x is in between 0 to 5 meter and it is 12x square, that is equal to 12 into 10 raised to 12, that is equal to 12x square into 10 raised to minus 3 coulomb per meter. So we have now dq is equal to rho L dl. So by taking integration, equation will be q is equal to integration goes from rho L dl. So in Cartesian coordinate system the variations are x is denoted by dx, y by dy, z by dz. Now the variation of x is given. So to obtain the equation of dl, consider only parameter which is varying, that is dl is varying, so dl is dx. Now this is equation 1. So put the values in equation 1. So we get q is equal to x goes from 0 to 5, 12x minus 3 dx. So it is 12 is taken outside, 12 into 10 raised to minus 3 is taken outside, and it is integration of x square x cube by 3 and it is 0 to 5. So by solving this we get answer 0.5 coulomb. Now the second part of the problem is given that 3 and z is in between 4 and 0 meter and rho s is equal to z square nanocoulomb per meter square. So it is rz square, sorry. It is r. So it is rz square into 10 raised to minus 9 as it is nano. Now we have equation dq is equal to rho s ds. So by taking integration we can write integration goes from ds. This is equation 2. Now to obtain the equation of ds, now it is a cylindrical coordinate system. So the variations in these coordinate systems are r is defined by dr, phi by r d phi, and z by dz. Now there are some rules to obtain the equation of ds. If the direction is given, then delete the component corresponding to the direction and take multiplication of remaining component. This is the first rule. And the second rule is if direction is not given, then check the coordinates which is constant and delete these components and take multiplication of remaining component. So in this case, here we write, in this case r is equal to 3, which is constant. In this case, r is equal to 3, which is constant. So delete dr and take multiplication of r d phi dz. So ds is equal to r d phi dz. Now put all the values in equation 2. So for solving it, we have to remember the two rules. Now q is equal to integration rz square into 10 raised to minus 9 r d phi dz. So it is r square z square into 10 raised to minus 9 d phi into dz. Now here the values of z is given as z is in between 0 and 4, and phi is given as phi is in between 0 and 2 pi. Here the variations, we can write here variations of z and phi. So we can write q is equal to 10 raised to minus 9, r square is constant, so phi goes from 0 to 2 pi d phi, and z goes from 0 to 4. Z square dz. Now we have r is equal to actually not r, this is rho. You can write here rho. Okay, you can write here rho. You just replace this by rho. It is equal to 3, which is given in the problem, so we replace it. It is rho. Q is equal to 3 square into 10 raised to minus 9 phi 0 to 2 pi, and it is z cube by 3 0 to 4. So by solving this, we can get it is into 10 raised to minus 9 into 2 pi into 1 by 3 into 4 cube minus 0. So it is 1.207 micro coulomb. Thank you.